Let's have a look at question 9 in this video. So we have now a different type of lamp, type B, which is known that the lifetime is also normally distributed. We also know that 22.66% of these lamps last more than 4,000 hours and 30.85% last less than 3,600 hours. What is the mean lifetime for these lamps? Okay, so let's write this data in statistics. What is this saying? We know that the proportion of having a lifetime greater than 4,000 hours is equal to 0.2266, which is the same way as 22.66%. With the same logic, we know that the proportion of having a lifetime less than 36 hours is equal to 0.3085, which again is the same as 30.85%. But recall that to find out the proportions, we must know the z values. So we're going to standardize this into the z distribution. So what we're looking for is the probability that we have a z value greater than, and now we're standardizing 4,000, which is the difference between the 4,000 and the mean of the lifetime, which we don't know, which we're finding, relative to the standard deviation of these lamps, which we also don't know, and that must equal to 0.2266. With the same logic, we have the probability that the z value is less than, and now we're going to standardize 3,600, which is the difference between 3,600, the mean of the lifetime relative to the standard deviation, and that's equal to 0.3085. Now, we already can find out in the table of the z distribution what's going to be the z value that gives us a probability of 0.3085. So if we draw this, we know that we're going to have a specific z value, and the probability that it is less than that number is equal to 0.3085, and that z value happens to be minus 0.5. So in the table with the z distribution, we can find out that for the z value of minus 0.5, the probability of z being less than minus 0.5 is equal to 0.3085, and that's exactly what we're looking for. So we already know a z value, but then let's work with the other z value over here, because here it's slightly different. Here what we have on a z distribution is a specific value. So we have a specific value, and the probability of having a z value greater than that number is equal to 0.2266. So that is the proportion that we're looking at. But recall that in the z distribution, we only have the values to the left of that specific number. So we need a z value that's gonna have the following proportion. And we can find out the following proportion because in total the proportion, the area under this curve must equal to 1, meaning that the green area is just 1 minus 0.2266. So we're subtracting the small tail, and that's equal to an area, a proportion of 0.7734. And the z value corresponding to this proportion is equal to 0.75. In other words, the probability that the z value is going to be less than 0.75 is equal to 0.7734. Or in other words, the probability that the z value is greater than 0.75, which is this area over here, is equal to 0.2266. So it's the two ways to look at the same concept. Now with this in mind, we can actually solve this system of equations, because we have the z value in the first relationship and in the second relationship. So we can take them together and we can find something better. So let's write this here below. Let me zoom out to make some more space, and we're gonna solve it right now. So let's write it over here. We have the relationship that 4,000 minus the mean of the lifetime divided by the standard deviation is equal to a z value of 0.75. We found out after we standardize, and at the same time we also know that 3,600 minus the mean of the lifetime divided by the standard deviation is equal to minus 0.5. So we're going to solve this system of equations. We're going to take them together. Now, how would we solve that? Well, first of all, let's do a cross product. Let's do a cross product on the first and on the second equation. So we would have 4,000 minus the mean is equal to 0.75 times the standard deviation. And over here we have 3,600 minus the mean is equal to minus 0.5 multiplied with the standard deviation. Now, what can we do here? We can add the following equations. Actually, we can subtract the following equations. I'm sorry. We want to get rid of one term. We want to get rid of the mean and then find out the standard deviation first. So if we subtract these two equations, what do we get? 4,000 minus 3,600, that's equal to 400, minus the mean, minus the mean becomes minus the mean plus the mean, which is just 0, so it cancels out. 0.75 minus 0.5 becomes 0.75 plus 0.5, which is 1.25 multiplied with the standard deviation of these lamps, of the lifetime of the lamps. Now, we have already the relationship for the standard deviation. We can calculate it. So we can calculate it over here. Standard deviation is going to be equal to 400 divided by 1.25, which is equal to 320, which is equal to 320. And now, knowing the standard deviation, we can substitute in either of these relationships. For instance, if we go to the first relationship over here and we substitute the standard deviation, we're going to be left only with one variable, and that's exactly what we want. So that's going to look the following way. 4,000 minus the mean is equal to 0.75 times the standard deviation of 320. So 0.75 times 320, that would equal to so just a second. So 4,000 minus the mean, 4,000 minus the mean is equal to 240. If we change the places, the mean goes on the right side, the 240 comes on the left side. We'll find out that the mean of this lifetime is going to be equal to 3,760 hours. And if we have a look at the answer key, it happens to be the same number. So the answer is true, and we are done.